So please carry one point with you: learning should never stop, right? Regardless of evaluation and other aspects, right? Whatever you can bring it to my, whatever I have something, I can do some tuning to that and see. But whatever you want me to, okay, tailor this way, that way, I can still, there are 4 or 5 sessions, whatever is the leftover time, right? We can do that. If I need to revise something which we have covered in previous sessions, maybe a bit here and there, you can even ask that. I am, but you have to put efforts for that. And in the second lab session, right, which Professor Omshiri conducted, nobody was there. This is what she told. And we are planning, right? She's not doing independently the things. Whatever I have covered, I am changing the time slot. Okay, this has been covered. You plan this way, these things, right? But there's no input coming to us. We are putting efforts for that, right? And it is only for you. And we want your interest to come. You try some exercise. You want us to give some exercises for practice, she will give. Not an issue.
Opposite.
Learning should never stop. That's what I would say. Regardless of whatever is happening, right, and what stage you are right now, it should never stop. Okay. So let me give you a refresher of what we were doing, right? Uh, Largely post mid semester, we have started with the decision trees, right? Decision tree is a classification model. So we all of us know about a tree. It has a root node, it has intermediate node, it has leaf nodes, right? When I say classification model, so you already know some discrete set of classes to which a particular record will belong to, right? So far, what we have been doing in machine learning, you have some training data, right? Historical data, which you will use for training. You have the mapped classes for each of the records. That is supervised learning, right? Today, I'm going to touch upon unsupervised learning also. So that is supervised learning. We have labeled data with us. And one of the supervised classification model is a decision tree model. We have talked about earlier, if you remember the logistic regression part, naive-based classifier. Then third, after naive-based classifier, we did uh, support vector machines, right? We talked about ensemble also. Sorry, decision trees first and then ensemble methods, right? So this has been largely covered, and all of these we have said supervised learning techniques because we have labeled data. The set of predefined classes are already known to us, right? So in decision trees, you have a tree like this. I can show you. This is one of the trees, right? So this is prepared from a data set. And we have covered techniques in order to prepare this entropy, Gini index, right? Misclassification error and other things. We have solved numericals also. But just let me give you a brief. Now, this, let me tell you from which data set we have used to kind of generate this. Do we have that? No, not in this. Maybe. So this data set was kind of, we are given some features, outlook, humidity, wind, temperature also. There were 4 features, and we are predicting whether I'll go to play tennis or not today, right? So it is a yes or no kind of a binary classification. So at each step, what we are doing a test on the attribute. Like I'm checking the outlook. Outlook could be sunny, could be overcast, could be rain. So accordingly, there are 3 branches, right? So if there is an overcast, the output is yes, regardless of any other attribute. So we are going to stop here, right? With this, with respect to this overcast branch, there's no need of further extending the tree, because if I see the target feature, it is yes wherever the outlook is overcast. So I need not to check any other feature. While for sunny, right, I might have some records which belong to yes and some records which belong to no. So I need a test on another feature, and I'm doing it for humidity. If it is high, it is no. If it is normal, it is yes, right? This is the second part. Third part, if the outlook is rainy, right, then I'm going to check wind. Is it strong or weak? Because at this stage, I'm not able to come up with a pure classification where all of them I can say they belong to yes or no, right? So I have certain records belonging to yes class, certain records belong to no class. So I'm checking one more attribute, which is wind. It could be strong, it could be weak. And if it is strong, I'm not going to play tennis. If it is weak, yes, I'm going to play tennis. Right? This is how. So this is prepared from a data set. There is a structured approach behind it we have followed that, okay, there are multiple features given to me. Right? Outlook is one, humidity is another, wind is another, right? There was one more, I remember, temperature, and play tennis is my predictor. It has yes, no values kind of a thing. Right? So out of these four input feature, which one to choose at the root? Why I've chosen outlook? Why not humidity? Why not wind? Why not temperature? So for that, we have a technique, right? Mathematical or statistical procedures, we can say entropy measures. Entropy is the randomness within the data. So at the first stage, without choosing any attribute, I measure the randomness of the data set. When I say randomness of the data set means if I have certain number of records, let's say 10, how many records belong to yes and how many records belong to no? If it's a 50-50 split, let's say 5 records belong to yes and 5 records belong to no, entropy is the highest. It's a completely random data, right? If I have 9 records belonging to yes, only 1 record belonging to no, entropy is less. If all of the records belong to yes, we don't need any classification thing. It's always yes, right? So entropy is 0 in that case, minimum, right? So what is the entropy of the data set? When I pick one of these attributes, outlook, humidity, wind, what is the entropy left out, right? We have covered these. If you remember, this is what we have covered. What is PI? Probability of a record belonging to class I. I have two classes in play tense, yes and no, right? So this is what I will compute when I pick a certain attribute. First, I will compute it for the data set. When I pick a certain attribute, then I'll compute it for that particular attribute. Let's say I picked outlook. For sunny, how many records are there? For overcast, how many records are there? For rain, how many records are there? How many of them belong to yes and how many of them belongs to no? Sorry. I need to expand that equation, right? And calculate. Whichever is giving me the lesser entropy when I'm choosing a particular attribute. Let's say the entropy at the start was 0.9. And when I choose outlook, it has reached 0.6. When I choose, let's say, humidity, it has reached 0.8. When I chose wind, it has reached 0.7. And when I chose temperature, it is, let's say, 0.85. So from 0.9 to 0.6 is a bigger jump, right? Rather than this. So I will choose outlook as the first attribute. We have to do these calculations and then arrive, okay, outlook will be the best. So we basically compute the information gain. This entropy minus this entropy. So this information gain is 0.3. This is 0.1. This is 0.2. This is even 0.015, something like that, right? Yeah. So this information gain is high. So I'm going to choose outlook as the first attribute. Right. Then again, at the next branch at humidity, right? Which attribute should I choose? Sorry, at outlook, I have reached this. Now, should I choose humidity or should I choose wind or should I choose something else? Again, the same set of calculation with those records which belongs to sunny now have to be done. At this point also with those records which belongs to wind, right, has to be done. And then we build a tree. So this is a bit of refresher what we have done. Details you can refer to your previous sessions. Please go ahead with your question. Yeah.
Sorry, sir, but you subtracted it from which? So I did not understand. My connection broke actually. You
I'm
got two
saying
and you subtracted it, right? So what is the second one that you subtracted it from?
you're saying this 0.9 and 0.6.
Yeah,
What are
the
these
point
values?
six, the point 0.6.
0.6. Okay. So one is the total entropy of the data set basis on how many records belong to yes and how many records belong to no. If it is 50-50 split, the entropy is more, right? If it is 90-10 split, the entropy is less, right? So that we can calculate the entropy of the entire data set first without picking up any attribute.
Of
What is
the
the
output,
entropy
right?
with, yeah, of the only the output feature. Yeah, this one. Basis this, because this will give me how many records belong to yes and how many records belong to no. In our data set, I remember, right, which we have chosen, there were 14 records, 9 belong to yes and 5 belong to no. The calculations
Okay.
which you will see in the previous slides, right? Now, when I chose Outlook, right, then what is the entropy? Again, I have to calculate. Outlook for Sunny, right, there will be some set of records. Let's say there are 5 records for Sunny, 4 records where the value is overcast, 5 records where, so total 14.
Yeah.
Then within these 5, how many belong to yes, how many belong to no, how many belong to yes, how many belong to no, how many belong to yes, how many belong to no. So I will calculate the entropies with respect to these 5, 4, and 5 records. Then I'll take the weighted one, right?
Okay.
And then I
Okay.
will arrive at this 0.6 thing.
Got it. Okay,
So
sir.
at each
Right.
step, I have to do that and then build the tree. My
Yes.
only sense was, right, what you could have tried, right, which I think, which I believe maybe, I don't see if any one of you have tried or not. There is a code, right, which is covered by Professor Omshri for decision trees. So you would have tried that 14 records of data set and see what kind of tree that you are getting it, right? And just try it with bigger data sets. Okay, what kind of tree? Because with 14 records, 20 records, 100 records, I may get a tree, right, which perfectly fits everything. But with, let's say, 1 million records, if I'm going to come up with a decision, the depth will be very, very long, right? Or the height of the tree or the depth, whatever you call it, that will be too high. And if that is high, of course, whenever I have to predict, I have to go through each and every, I mean, I have to go through a certain path and then make a prediction. The computation will be high, right? And moreover, when I build a very deep tree with a high depth, it may end up in an overfitting. I want a generalized model. I don't want overfit model because I am always using certain data, right? I have to do predictions on the unseen data. I don't have to come up with, maybe I don't need to target 100% accuracy every time, right? So depending on the domain in which I am building, right, there are domain experts from where I can say, okay, what kind of accuracy we are targeting, what is the depth, that these are all hyperparameters, right? That's why I always say, understand the base first, take, okay, with smaller data sets, experiment it, and then pick up something from the organization, try to build around it. That will give you a ample learning. We've covered multiple models, right? And there is a now a differentiation also created. I'm delivering the conceptual part, another professor delivering the practical sessions and all, right? And we are planning it also, but response has to come back to us, right? She also has a similar concern when I spoke to her, and I'm also facing the similar thing, right? So if you can avoid for last 4 or 5 sessions, it will be good, and you can revise your older ones also. And anything you require from our end, we will definitely help you out. Okay, then there were, I mean, there were concepts discussed. What if there is an overfit tree, right? There's a concept of Occam's razor, which we have covered, which I don't want to go into it again, but it's a simple thing, right? We can reduce the tree depth that is shown in this example here, right? If you look at this particular age is there, right? We are testing another attribute here. Do we really need to go about it or not? That we have to think, right? And if you look at this proportion, again, we are testing age here, right? Do we really need to go about it or not? What what provokes us, okay, let us not go for it. Maybe it is leading to an overfitting model. At this stage, let's say, if I talk about this pruned tree, right? Pruned is, this is the original one and this is the pruned one where we have merged certain leaf nodes. At this moment, right, if I am getting, let's say, there are 1,000 records falling here. 995 records belong to one class, let's say yes, and some 5 records belong to no class, right? So majority of the records are belonging to this class. So I can stop here. When whatever the new record falling in this path, I will classify it as yes. I'll classify it as yes. I want to keep it more generalized. I don't want to overfit it, right? Just for the sake of 5 records in 1 million, I am trying to create another branch, right? I'm just giving you an example. Again, this thing, domain expert will input you, or you have to experiment it yourself and see what it is, right? This is what is there within the machine learning, right? You have to experiment it a lot and then come to the conclusion. And that is what makes you understand with respect to how different data sets are behaving or how this particular algorithm is behaving on a particular data set. We have covered around 5 classification algorithms. Right? If you pick up a data set and try to apply all of them and see which is giving me the better performance and why, that is going to give you ample learning. And that's what we have put in the assignment for 2 models. Right? So this overfitting concepts, you can just go through once again the session recording. And if there are any doubts and anything, right, you can always write an email to. Learning should not stop. Ensemble methods we have covered. I'll just give you an idea of ensemble method. We have used different classifiers, right? Naive Bayes is one, decision tree is another, SVM is one more, logistic regression is another. So what ensemble says is, I'm going to come up with multiple classifiers, right? So look at this. There is a data set. I'm going to divide my data set into multiple parts, and I am going to train one classifier out of each data set. Look at this. And then I'm going to combine the result of all the classifiers to make the final prediction. Maybe I'll say, okay, this classifier is giving me a vote of yes for a particular record. This is also giving me yes. And if majority of them are saying yes, I'll classify it yes. If majority of saying then no, I will classify it as no. So I'm talking about a binary classifier. It could be multi-class classifiers also, right? So ensemble is training multiple classifiers and getting the predictions from multiple classifier and then combining it, right? We have come up with 2 techniques, right? So this is all stats, that if every ensemble has an error rate of 0.35, you have 25 classifiers which are identical, they will vote the same way on each test instance, and then the ensemble error rate is also same. So we want diversity in all those classifiers. It's not like that everybody voting yes, right? All 25 are voting the same. Then it is of no use, right? I mean, whatever the error is there within one classifier, the same error will come in ensemble also. But if there is enough diversity in all, right? If they are independent. So then ensemble will make a wrong prediction if more than half of them predict incorrectly, because I'm taking majority voting. If there are 25, if 13 of them will predict it wrong, then only the ensemble will go wrong. Otherwise not. So this statistical thing says, right, the chances of error becomes 6%, then the 25% if they are all the same class. That's the beauty of ensemble, right? So you can compare the ensembles with the Bayes classifier and see how does it works, right? This is a graph. We have talked about it earlier also. There are techniques, right? How to construct an ensemble classifier. I can manipulate the training set. I can manipulate input features, class labels, learning algorithms. So there are multiple ways to come up with ensemble classifiers, right? Training set is different. input features, I'm going to vertically split my data set. I'll give certain set of features to one classifier, another set of features to another classifier, right? Depending on class labels, basis, okay, I am going to give more class labels to this. So this will predict this kind of class label largely, right? So then learning algorithm could be different. It's not only all decision trees are being used, right? Maybe something different can also be tried. There are techniques like bagging and boosting, which we have done, right? From the same data set, we are coming up with different data sets, like this is bootstrapping that we are doing, right? Bootstrapping, we use it within bagging. Bagging is bootstrapping aggregation, basically. This is initial data set, right? And you can come up with some bootstrap data sets for this, right? So I'll show you that particular slide. Look at this first bootstrap. This is my original 5. Let's take an example of 5, right? So bootstrap dataset is, you see this particular record, right? And this particular record has come twice, right? Even this record and this record has come twice. So randomly you pick it with replacement and come up with a bootstrap dataset. So that my dataset becomes little different. So I am going to train with one bootstrap dataset. So I can come up with multiple bootstrap dataset and train one classifier, and all of these are known as weak learners, right? Weak learners. And then I can combine the output of, see, I'm training it, one weak learner, another weak learner, another weak learner. And this training can happen in parallel. So which reduces that training time, kind of, right? So you have F1F, F2X, and F3X, and then you are taking the average of it, right? So this is ensemble can be used for regression also, where you are predicting continuous variable. So you can take the mean of that, right? When you are doing it for classification, you can always pick up the majority voting kind of thing, right? Weighted votes can also be done. We have discussed all these things. So bagging also, these are the examples which we have discussed last time, bagging and boosting examples. You can just go through the recording. If there are any doubts, you can always come back. So you look at this classifier, basically what it is saying, the first classifier is saying, so you have 1 and -1, right? So first classifier says if it is less than 0.35, 1, greater than 0.35, -1, though there is some error that you can see, right? Second classifier, right? Bagging ground 2 we have done. So this is, now you look at this, there are 3 ones here, there are 4 ones here. So it will learn like if it is a great less than equal to say 0.7, the average of these two, right? It has taken 0.5 and 0.9 average 0.7. So it says y is equal to 1 and greater than 0.7, y is equal to 1. So it has taken y is equal to 1 here. Reason is, see, 3 ones, 3 -1s, 4 ones here, right? So it is everything, it is kind of classifying into 1. It could be -1 also, but it is class. Let's take it 1 as of now. If you look at the third one, right, 0.35 it has taken, average of these two. Greater than this -1, because -1s are more on this side, less than this +1. So that way we are kind of learning everything, right? And what we are doing here is further, these are the round of 10 data sets, right? Bootstrap data sets we have picked up, bagging things, and split points we have written, left class, right class we have written. So if I have to now make a prediction, right? Look at this. We are just going to sum this across, right? Sum 2, it is just for this specific problem because it is 1 or -1, right? Either the prediction is 1 or -1. So each of them you treat it as a classifier, right? The prediction is 1 or -1. We have only two things. So if I sum it across, if this is positive, right, actual predicted class will be positive. If it is negative, actual predicted class is negative, right? So you see, for all positive, it is 1. For all negatives, it is -1. Now, if you look at this, there were some errors in each of these, right? Each of these. This is my actual original data set, right? This is my actual original data set. And this is the split 0.3 less than this plus 1 greater than 0.8 plus 1 and 0.4 to 0.7 minus 1. This is the classifier, right? In between. Now, if I pick up this triple 1 minus 1 minus 4 times minus 1 and triple 1, this is what I'm getting, right? When I'm actually predicting. See, even though each of the classifiers has some error, but when I'm taking the ensemble of all these, you see the accuracy has increased. We've covered it in detail in the last session, right? You can just go through it again, but this is what the accuracy is. Are you able to follow or not? So different classifiers, we are learning different boundaries, right? Each of them have some error. If I talk about this, right, it says less than 0.351 greater than 0.35 minus 1. But for what about these two? This says both sides 1, but what about these three? So there is some error, right? So 30% error is there. Here also 20% error is there. Here if I look at less than 0.35 greater than 0.35. So again 20% error is there. Look at this, less than 0.3 greater than 0.3. So again 20% error is there, right? So every classifier, individual classifier has an error, right? But when I take the vote, so I am classifying as per each individual classifier. So first classifier gives it as 1, right? Second also give. So first five classifiers will give it as -1. 6, 7, 8, 9 give it as -1. Last one it is giving it as 1. Now I am taking the ensemble, majority voting. So if the sum is +2, of course, more classifiers have voted for +1 rather than -1. Right? So this is ensemble, training multiple classifiers, right? And then just check the vote of each classifier and then categorize it. So it is reducing error, you can see. This is algorithm, right? So we have covered all these techniques again, right? I am not going to the details of this AdaBoost thing. You can check it out, what exactly the similar kind of thing, but with some weights and some update method is there, right? Which we are using. You can just learn bit of calculations. Don't go too much deep into the mathematics, right? And this will help you to understand what exactly we are trying to do with all these techniques. The things will come when we are not doing in either you learn the core mathematics of it, right? Which is not the objective in this course also, right? This is applied part. So more things will come out. Now you have covered, look into this, right? AdaBoost, right? You have covered this bootstrapping, bagging. Try all these methods on some data set and see what is happening. What kind of accurate? It's simply a library calls when you do that, right? Simple library calls are there. And on the similar concept, this algorithm random forest, which is a part of your assignment, right? That you need to train on come up with the performance of random forest also, right? And then you have to comment, ensemble, and this random forest things, which is giving you the better. So you see this is the comparison being made. Number of attributes, classes, instances, right? This is all the data sets which are available. And this is what is the parameters that we are getting. You can say the kind of accuracy that we are getting. Decision tree has given this much accuracy on this data set. Bagging has given this. Boosting has given this. Random forest has given this. So we want you to do something on something similar on a data set that is closely related to your workplace. And when you do this, right, you then try to analyze data sets also. What kind of properties this data set has, right? And why this particular technique is working better. some learning, then you will get. Otherwise, implementation for these kinds of things is very straightforward. Nowadays, LLM is there, which can give you the code, but you need to understand that code, what it is trying to do, what I can do differently. It's a bit of hyperparameter tuning that we can do, right? Because every data set is new. Do you think one model that we have trained as classification generalized model and it will work for every data set? Do you think that way? If I've trained something on financial domain, right? Do you think the same will work on the retail domain? Because both domains are different. Their objectives, which particular feature will impact more, right? Maybe nowadays, if you see CIBIL score in financial domain for a loan approvals, right? That plays a major role. That gives ample history, right? Within the retail, maybe what is the shopping behavior of the customer? That also, which feature impacts more, right? That is feature engineering, which we have already covered before mid semester. Correlation things and all we can do and come up, okay, these are the features which are of prime importance. So whenever you do, okay, you are trying to understand the concept, make notes, right? Go through the recording, or if you find some other resource better, right? Where you can understand, okay, you want to come up with some questions, come back to me, right? Write it to me, we can discuss. And then also very, very important aspect in order to gain the practical learning is start with a smaller data set, maybe the way we have covered that you can generate those kinds of data sets even with Python, some 15, 20 rows, and try that algorithm. Try that algorithm, how it is behaving. Try to understand, okay, if I'm changing this, how it is behaving. If I'm doing this, how it is behaving. Spend some time on that, 2, 3 hours. Then pick up a bigger data set and apply all those algorithms and see now how it is working. That is going to give you a learning. Concept is fine, plus the implementation. It is very, very important. So this is what we have done right already. Let me touch upon just a minute. I'll just give you some other visual. I have slides ready for that, but let me give you some other visual from where you can easily understand, right? The unsupervised learning part. Just give me a moment, right? I am searching for those slides. Uh, the things are not very difficult to understand, right? But effort is required. Okay, can you see the slides? Okay. May I have response from others, please? So in the session one, we have talked about what is machine learning, right? Broadly, what has happened? Again, it has come back. Why I'm not able to write anything? Just a minute. Okay, got it. Yeah, fine. Now good. Okay. Are you able to see the blank screen?
Yes.
So if you remember, broadly we said, right? Broadly, there's unsupervised machine learning, there is supervised, right? So we have spent enough time on this, right? We have covered two kinds of problems, if you know, right? So first is the basic concept is we have a labeled data. We don't have a labeled data, it's unlabeled basically, right? Let's say if I am predicting something, right? I have to predict, uh, let's say, whether the given picture is of, let's say, a cat or a dog, let's say, right? I have some, let's say, images already with me, some 1,000 images already with me, right? For which, let's say, some 600 images are of cat and some 400 images are of dog, right? I know, okay, I have a data of 1,000 pictures where 600 are dog, 400, sorry, 600 are cat, 400 are dog, and I am feeding it to a classification model. Model will learn the features of cat, features of dog, and then when I'll give it a new picture, it will predict whether it is a cat or dog. So I have fed this labeled data. Why labeled? I had certain features of the images, and I also had the categorization that this is cat and this is dog. This is cat and this is dog. Now go back to play tennis example. I have four features with me: outlook, temperature, humidity, and one more, wind, right? Wind speed. So I have four features with me, and I also have a play tennis yes or no, using which I am calculating entropy and other things, right? So that label, whether I go to play tennis previously with these four options or not, is with me right now. So when I have that labeled data, it means the desired output, the target feature is available. That is there, right? It means that is a supervised learning problem. So using labeled data, what we have done is classification, as well as if you see regression, that was your lab sheet one. House price prediction, stock price prediction, because I am predicting a continuous variable. But again, what I was having certain house price data. What are the number of bedrooms, right? Available with me, then size is available with me, uh, proximity to nearby market and so on. That is available with me. And then I was having a price. Okay, this house is of, let's say, 50 lakhs. This house is of 70 lakhs. This is available with me. So this is labeled data. When I'm doing training with the labeled data, that is supervised learning. Now imagine I don't have this. Imagine I don't have this, right? I only have a set of 1,000 images with me, right? That is unlabeled data. I don't have the categorization. I have the data set with me, but I don't have the categorization. So I don't know the predefined set of classes. What can I do now, right? So when I'm not dealing with the labeled data, still I want to do some grouping and all, that is unsupervised learning. And we use clustering technique in order to group those people or those data points. So images which are similar to each other, that will be grouped under one head, and which are different, that will be grouped under the. So all cats images will be under one group, all dogs images will be under one group. That is done based on the similarity of the images with respect to each other. Obviously, if it is a cat image, right, the features will be same. Some of the features will match, right? And basis that, the algorithm tries to identify, come up with certain groups. Okay, these are the number of groups that I can come up with. Let's say if it is cat and dog, so it can come up with two groups, and these are the set of images which are similar, and these are the set of images which are similar, but they are different from each other. So it will do some similarity check, and based on that, it will try to come up with certain group. It could be two groups, it could be three groups, it could be five groups, depending on how it learned, right? And that is unsupervised learning. And one technique that we are going to cover today is clustering. Nothing but, again, I don't have the predefined categories that I was having with the classification. The target feature is not known to me, but based on the input set of features, I can come up with different cluster. Cluster means simply groups, but in machine learning terminology, you will see this called as a clustering. So did you get an idea what is the difference between classification and clustering? Does it make sense? Yes or no? I didn't get to hear. Some people, few people unmuted, but I didn't get to hear that.
Yes, sir. Makes sense.
Is it making sense to everybody? Vasu? Ali has confirmed over chat as well as verbally. What about others? Vasu Gupta, are you there? See, mentally, you also need to be present, right? Response should come immediately. In an online classes, there's a self-motivation required. Any other candidate? Any doubts? Because this is the baseline that we are setting now. Difference between clustering and classification. Because classification also about categorizing, right? But the categories are known to me from the historical data. Here also it is, I'm not saying categories here. I'm saying different groups, but those number of groups are not known to me. That algorithm will find out by finding out the similarity between the different data points that are given. Data points is data set, right? So clustering, it's an unsupervised learning because the class label information is not present. It's a form of learning by observation, right? Now, okay, let's look at this image first, right? Input data is given to us. We don't know the classes, right? But what it will do, right? You see here, you don't know what is the category of this, what is the category of this, what is the category of this, right? But what it has done, see, if I give it to some clustering algorithm, it has separated out this. It has come up with three groups. So these four images look similar to each other, so they are put into this. These two images look similar to each other, so they are put into this. The three images look similar to each other, they are put into. So it has come up with three different groups. but we don't know the category, right? So these are previously unknown groups. Now you have made groups and you want to label them, you can do that, right? This is what clustering will do. What is important now? Now, if you look at this, right, there are three circles that you can see. Within those three circles, there are some smaller circles that you can see. So this shows there are three groups being made. 1, 2, 3 from a particular data set. So I have visually plotted if it is a 2D data set or 3D, right? Up to 2D, you can better plot and visualize it. And if you can visualize it, this is what it is. It has come out. And if you look at this, right, there are three different groups you see which are circled. The idea of clustering is the points, data points, which are belonging to the same cluster, the distance between those points should be minimized, while the distance, I'm using the term distance, right, between the points belonging to two different clusters should be more. Only then it makes sense, right? Otherwise, these clusters will overlap. So intra-cluster distance, meaning that the distance between 2 points belonging to the same cluster should be less than the distance between the 2 points belonging to different clusters. So if you see this distance should be smaller than this distance, right? If you say, okay, the distance between 1 point here and 1 point here is lesser than the distance between this point and this point, then that's not a good form of clustering. What we are trying to do, it belongs to one group, but it is far from the data points belonging to other group. Only then it's a well separated clusters, right? If I am getting these kinds of circles, right? So it's kind of overlapping. I cannot come up with any decision out of it, right? I hope it makes sense. What is the basic definition? And when I say distance, right, it's more of similarity. So why I'm saying distance here? I'm assuming as of now, let's say all my features are, let's assume they are numerical features and I can plot it like this, right? And of course, Euclidean distance, which we have covered earlier, right? That okay, x1p minus x2p kind of scale, right? Which we can do plus the y variable we can do. Right? Scale of, we have to take the difference of the scale of the corresponding features, take the square root of that, right? That is what Euclidean distance is. This is what also we have covered. So this helps us to find out the similarity, right? If that similarity is more, the distance will be less. If the similarity is less, it means they are highly dissimilar, the distance will be more. So objects belonging to two different clusters should have a larger distance than the objects belonging to the same cluster. Only then it makes sense. Otherwise, overlapping groups does not make any sense. We want well separated cluster. Does that make sense? Does that make sense why overlapping clusters will not help? May I have some response, please? Hello? See, this is what I do not like it, right? People should respond. And if there is any question, please raise hand and ask. It is your time. Clusters should be as distinct as possible. Exactly. When you give such statements, right, it also gives you, now you have understood. Okay, now I can move. If there is no communication happening, right, I don't know what you have gained out of it, what I've spoken. So unsupervised, we know, right? So what is the application of clustering? Now let's say company want to do some target marketing, right? for a new product which it is going to launch, or which, right? Marketing comes up with a cost. So maybe now this product, they want to find out the target audience, right set of audience for this, so that they can reduce the marketing cost. They don't want to market it to everybody because it may be a high valued product. So doing marketing for it to maybe a low spend customers may be meaningless and it will incur cost only. So I want to come up with some different group of customers, right? Whatever data I have, I can club them into different groups. I can put them into different heads using clustering algorithm. And then when I'll find out this is high income group, and basis that, okay, what kind of product they have purchased in the past, right? They're likely to purchase it. So let me target this particular group or these two particular groups out of 4 or 5 groups that I have come up with. So it is going to save my cost. So this is market segmentation, right? So you are trying to determine the appropriate audience for the new product that is being launched. Land use, so identification of areas of similar land use in an Earth observation database, right? I want to find out those similar areas, right? So I can do clustering in that. Identifying groups of motor insurance policy holders with high average claim cost, right? So maybe people have seen some patterns, right? So they want to find out such people. This should be the average claim. And now I want to find out those customers or those insurance policy holders with more than with a claim higher than the average claim, right? So it's again, if I take the example of that examination team has come up with certain rules, probably there is something gimmick they have found out and they want to change that policy, right? So these kind of things, why this is happening, they will deep dive and then they will come up with some new rule to it, right? City planning, identifying group of houses according to their house type, value, geographical location, earthquake studies, observed earthquake epicenters, and should be clustered along. So there can be different applications, right? You can also find out some applications related to your work where you can do clustering, right? You have to also understand whether you should go for classification or clustering. So you see what kind of data set that you have. If you don't have any labeled data, only then clustering will make sense, right? These are some more examples, right? Image segmentation, distribution of data, outlier detection also sometimes we do, right? Outliers are the data objects that behave very differently from the other objects, right? So one example, if I take, right, let's say the average CGPA is 6.5 or 6.8. One of the candidate is having 10, another candidate is having 3. So these are the two outliers. These are the two outliers. I hope it is making sense. People are leaving. Okay, Ali has left. Anybody else who would like to comment? Is it making sense? Applications of clustering? Okay. The second thing comes up is, if you see a data set, what is the natural grouping that you can come up with, right? You've seen this data set, this different set of images that you can see, right? One person may say, okay, I can say this is a set of females and this is a set of males that I can come up with, right? Another person may say, no, this is one family, and maybe these are some school employees within that. So that's another form of grouping that I've come up with, right? It's very subjective, right? It depends on the business of exactly. And secondly, notion of clustering, right? How many groups should I make? Should I stick with 2 groups, 3 groups, 5 groups? That's another challenging thing within the clustering. That is another challenging thing that we see. Look at this. This is the example. Now, when you look at this, right, this data set, this is complete data set, right? Now, one of you may say, okay, this is one group and this is second group, right? These are the 2 clusters that you can see. One of you may say, no, there are 4 clusters. You might put this into one, this is second, like this into third, right? And this is fourth. And maybe one of you may say, even you divide this into 2, right? This is 1, this is this 4 into 1. So total 6 clusters will come up, right? So determining the number of clusters is also very, very important. How many clusters should I come up? There are metrics which we measure. At 2 clusters, this is the quality of clustering. At 4 clusters, this is the quality of clustering. At 6 clusters, this is the quality of clustering. And basis the domain in which I'm operating, I can have the input from the domain expert and then take a call. Okay, these number of clusters are appropriate for this data set. Look at this types of clusters also. So these are very well separated clusters that you can see. These are also kind of more, but bit of joining with the others, right? So what is these circles are the centroids representing the clusters, right? This you can see another set of clusters, right? It's a different shaped, right? Not a very well separated kind of things, right? Now let us look at so what we are going to cover in this course is these are different clustering methods. One of the methods that we will cover is k-means, right? That's one only thing. This is we cover it in some other courses, right? These clustering techniques. Within k-means, we will also cover Gaussian mixture model after this, right? That is not listed here. Gaussian mixture model. Don't worry, I'm just giving you the name because I'm just going to cover k-means here because it from this slide deck, it is more detailed here. But whatever the slide deck which we have prepared for the applied machine learning, right? That will have k-means plus Gaussian mixture model, right? So let me directly move to k-means. K-means is basically, and now I'm going to cover this partitioning based method. Partitioning is kind of where I should make a partition, right? So those are partitioning based on distance measure. I'm going to take a call. So this is Euclidean distance, right? Measure. This is Euclidean distance. This is Manhattan distance. This is Minkowski distance, right? Cosine similarity that we use for measuring the similarity among the text data, right? Among the text data. So k-means algorithm, right? It's a centralized based technique. Let's go to the diagram so that we can understand what exactly it means. Yeah, look at this. Right? This is my data points, which you can see. Roughly how many clusters you can see. This is a 2-dimensional data set, right? These are the data points, the blue ones that you can see. How many clusters you see from a visual angle? It's a very simple question, right? How many clusters you see? How many groups you see? I'm not asking a very perfect answer. How many groups you see within the data set? See, that is the problem with the batch, right? You don't want to answer. What will happen? It may go wrong, right? Do you think that you should know everything right from the beginning? But we will understand. Give an answer. How many clusters do you see? Vasu Gupta, can you write your answer? Shweta? Four to five, you can say. Okay, fine. Shweta, Lakshmi, people should give answers, right? What is stopping you from not giving an answer? Yes, I'm unable to hear. Five clusters. Okay, good. So you can see five different dense groups coming up, right? Now, Vasu might have said, okay, these two can be clubbed, or we can even create a separate clusters. Fine, that is okay. Right? So we can roughly say five clusters, right? Now, when I say K means, K stands for the number of clusters that we have. When I say five, so there will be five clusters. If I say four, there will be four clusters and so on. So depending on the value of the K, the algorithm will operate and create those many groups. Make sense? What is the value of K? It could be 3, 4, 5. The number that you will give, it will come up with those clusters. Right? Now, how does K means start? Let us assume five clusters, as two of you said. Okay, five can also be there and five, right? So K means says, okay, I'm going to pick up five random centroids. So this is one centroid or the red dot, which you can see. There are four more centroids, right? I'm highlighting them. All are centroids. Some random points we have chosen as centroids. Now what will happen? There are some other points also. There are some other points. Now these points are representatives of the groups. These are cluster representatives or the group representative. Now, whether this particular point, right, which point is here, it should belong to this group or this group, how should we decide? Or maybe from the other three, right, also. The point here, should it belong to this centroid group, this centroid group, this centroid group, or this centroid, or this centroid? What I'm going to do is I'm going to find out distance of this point with this, distance of this point with this, distance of this. So I'm going to find out the distance of one point with all the five centroids. To whichever distance is minimum, right? Like you see, this distance seems to be minimum. So I'll allocate this point to this particular centroid. And this exercise I'm going to do for each of the points within the data set. So I'll measure the distance of each point with the 5 centroids because I've chosen K as 5. To whichever centroid it will have a minimum distance, the point will be allocated to that cluster or that group. Does that make sense? This is step number 1. Does that make sense or not? Vasu, Shweta, Lakshmi. What if it is in the middle of 2 clusters? So you are saying there is a point which has a distance of 5 from centroid C1, distance of 5 from centroid C2, right? How should I assign the point? Okay, good question. Sir, we use correlation as well, right, among the data points. For what purpose? Can you speak, please? For what purpose?
So while deciding which points are to be noted down around which points, like the
Mm,
heat map also provides, right? That these features are similar and these should be clubbed together.
no. Correlation does not give you these two features as similar, right? Correlation gives you when you find out correlation between two features, or right? If one feature is increasing, the other is also increasing, right? That correlation value will tell you. So correlation value between two features, if it is 1, right, means they are highly correlated. Highly correlated means if one is increasing, other is also increasing, right? If it is 0.8, they are positively correlated. If one is increasing, other is also increasing, but the degree of increase is not that much as you see with the value of 1. When two features are negatively correlated, they will have a minus value of correlation. It means one is increasing, other is decreasing. Here we are not doing anything like that. That kind of exercise we do in feature engineering, right? When we try to find out correlation between individual feature with the target feature, right? Specifically in supervised learning. Here what this algorithm is completely distance based. I am going to find out distance of a particular point with respect to the 4 or 5 centroids, the number of clusters I have chosen. Which one will have a minimum distance? I am going to assign that particular point to that centroid. Make sense?
So, sir, highly correlated does not mean that their feature will be similar. Like there will be similar data points.
See, you are mixing 3 things here. Let's talk about a structured data set, right? I have this kind of data sets, right? CSV files we have got. The first row is normally column headers, and then second one, the actual values start. This is data object D1, this is D2, this is D3, this is D4. Attribute, let me name it as A1, A2, A3, A4, A5, right? Now, if I ask you where you are you finding the correlation between data points D1, D2 or the attributes A1, A2? Attributes or the features,
The
whatever you call them.
D1, D1, D2.
D1, D2. So we never measure the correlation between data points. It's always with attributes, whether these two values are correlated or not.
Okay, so whether two features are correlated or not, that we look into.
Yeah,
That does not go.
that we look into, but D1 and D2 they are correlated. That is not making much sense. Because this is different data object, this is different data object. Whether they're similar or not, that we can make a comment, right? But now let me give you an example here. Let's say I have a data set that how much score a student will score in applied machine learning. There are input features like number of hours studied, self-study hours, right? He's putting number of classes attended. And whether he'll pass the course or not, right? Or let's say the score value. Now I can find out a correlation. Okay, number of hours studied, if it is more, high chances to get a high score, better score, right? A number of classes attended, let's say, right? And there's a high chance to do this. So I can find out a correlation between these. I'll find out number of hours every student has put and the score they have. And then I can find out a correlation between these two. The number of classes they have attended and the score they have. I mean, what is their score? I can find out a correlation between these two. But can I find out a correlation between these two? Okay, what Vasu Gupta has scored and what Shweta has scored? These are totally different, two different objects, D1 and D2. D1 may be Vasu, D2 may be Shweta. I am putting correlation between features, not between the data objects. Make sense, Vasu?
Yes, sir.
So when you ask a question, right, now I have to come up with different example and all those. So when you ask something, it makes your things clear, right? Maybe if somebody else also in the same line, it might have helped helped him or her also, right? So I'm just going to compute the distance here. Whichever will be the minimum distance, I'll allocate the point, right? This is step number 1. No correlation, nothing. Like a row in an Excel is one data point. Yes, that is one data point with related features in the columns. Yes, those will have the values, right? A1 will have certain value, right? A2 will have a certain value for object D1. A3 will have certain value and all. Yeah. So correlation you will have to measure. Okay, whether if student has attended more classes, is he scoring more or not? That is the correlation we can find. If it is positive correlation, it means that more the number of classes you attend, better the chance of getting a better score. Make sense, Ali? It does or dies. Concept should not die. Okay, anyways, fine. Then let's move to the next step now. Okay, so we have found out the distance of this point with respect to all the centroids, and I'm going to do this for all my points in the data set to find out the k-mean. Now look at this, right? What has happened? You see, these were the 5 points we have chosen. This is centroids, right? I'm just naming them. So we have made boundaries in the next. This is just a random boundary, right? Random, how I'm saying this boundary? When this is the centroid, right? The points which are allocated to this particular centroid are the ones above this boundary, right? Above this boundary, these are the points which are allocated. How do you compute that? These are very small points, right? You can always apply the algorithm and it can give you this. Okay, these are the points that are allocated to this centroid. And what are the points allocated to this centroid, right? The points which lie in this boundary, right? One line this, another line this, another line this. What are the points allocated to this centroid which lie in these boundaries? What are the points allocated to this centroid? This is the line, right? And this, whatever these points and these points. Points allocated to this centroid are this, and this within this boundary. So this is iteration number 1. So within first iteration, what I have found is this is as one cluster, right? All these points. This is as another cluster, all these points here. This is as third cluster. This is as fourth cluster. And this is my fifth cluster. Right? This is first iteration. It is not the end of the algorithm yet. Now, what is the next step? Now, there are some points here, but all belong to one cluster. But this is not the actual representative now, right? Centroid means which lies in the center, right? So now I'll compute the new centroid. How I'm going to do, whatever the points belong to this cluster, right? I'm going to take the average of the corresponding features and get a new centroid. So I'm going to do the average of this point corresponding features of these points, average of corresponding features of these points. So average of this, average. So these centroids will now shift. Now I will come up with new centroids. How to compute? Now there are, let's say, 50 points. 50 points have x value and y value. I'm going to take the average of all 50x, x1 plus x2 plus x3 up to x50 by 50, y1 plus y2 plus y3 up to y50 by 50. I'm going to do this average for all the 5 clusters. And now you will see these centroids are moving. It was here, right? Since some points lie here, it will move bit here, right? So you see this centroid was here, since bunch of points lie here. So it is moving towards this, right? And for this also, there's some bunch of points lie here. So this centroid is also moving towards this. For this also, there are some bunch of points lie here. So this is not a true representative. So it is moving here. And there's a smaller movement in this case. So in the next iteration, when the new centroids are computed, it is moving, right? The centroids are changing. Now, what is the next step? Now, these are my new centroids, the green ones. Green ones are my new centroids. What I'll do? Again, I will recompute the distance of every point with the new centroids now. I'm going to recompute the distance of every point with new centroids. And basis minimum distance, I'm going to allocate those points. So there may be some shuffling of the points from one cluster to other that you will see now. Because the point has changed, right? So there may be some more points which lie within the vicinity of this cluster. There may be some more points which lie or which might go out of the vicinity of the cluster because there is another centroid which is more near to some of the points which right now falls with this centroid. So those shuffling of points will happen, and let's see that one. Right? So look at this. This shuffling is happening, right? So this is moving a little more higher, right? And now with respect to this, I am going to compute the distance among all the points. And with respect to this, I'm going to compute the distance of all the points. And this will keep on happening. So again, there will be new set of clusters that will come with these as centroids. New set of clusters because some data points will move to some other clusters, right? So new set of clusters will come. Again, I'll compute the new centroids, right? Again, I'll compute the new centroids, and this will keep on happening. Let me see if I have some diagram here. Look at this, not this. This is all numerical, right? So okay, I think that slide is missing. That's a very good visual. I'll find out and I'll give it to you. Step by step, it shows how the centroids are moving, and within 5 iterations, the algorithm converges. But the idea is, let me tell you, the idea is find out new centroids every time, right? By taking the average of those points which belongs to one cluster and keep on repeating it. Till how much time you will repeat it? Every time there will be a new centroid, because now the points will shuffle, again the centroids will change. Again the points will shuffle, the centroids will change. The moment it stops shuffling the points from one cluster to another, when that happens, you actually stop your algorithm. There's no movement. So you have got your final centroid representatives, and these are the 5 clusters now you have. Right? These are the 5 clusters now you have. So let me take an example here. Let's solve. Let me give you an idea how this will happen. There are 5 data points: A, B, C, D, and E. Very simple example with 5 data points, right? Now, the very first step that you will do is you have find out the Euclidean distance matrix, right? Now, what is given to us is, look at this. We want to come up with 2 clusters. So K is equal to 2. Only 2 clusters. Because we have 5 data points, let us cluster into 2. So we have found out the distance of every point with respect to every other. So for distance of A to A is 0, A to B is 3.16, A to C is 3.61, A to D is 2, A to E is 5. So B to C is given, right? B to D is, it's not given. Basically, I can compute it using Euclidean distance. If I have to find out distance between A and B, how I will do? It is 3 minus 0 square, right? Plus 0 minus 1 square. So 3 square is 9 plus 1 square. So square root of 10. So 9 square root is 3. Square root of 10 is 3 point something. So 3.16. Right. If I have to find out AD distance, it is 2 minus 0 square plus 1 minus 1. So it is square root of 4. So it is 2. Right. So this way you can build this matrix first. Now randomly choose 2 cluster centroids. It may be given to you for the exam purpose. It may be you might have to choose. It may be from the data points which you already have. It may be separate from that. But for this example, we have chosen A and C as cluster centroids. So 0.01 and 0.24 are chosen as cluster centroids. These are the 2 centroids which we have chosen. Now basis this, I have chosen A as one centroid, C as one centroid. Now I have to allocate these 5 points, right? So obviously A will be allocated to A itself because its distance is 0. C will be allocated to C itself because distance to itself is 0. Now I have to check from B, D, and E which one should be allocated to point A, which one should be allocated to point C. Now I will check first the AB distance, distance of A with B, right? Now second I will check the distance of B with C, 4.12, which is smaller. 3.16 is smaller than 4.12. So I will add point B to cluster A. Now let me check for point D. Point D has a distance of, let's check it from A. It is a distance 2. From C, it is a distance 3. Again, 2 is less than 3. So I am going to add it to this cluster, right? And now let me check E. From A to E, the distance is 5. From C to E, the distance is 1.4. So 1.414 is less than 5. So I'm good. So these are the 2 set of clusters that I've got initially. Does it make sense? The first step, I've chosen 2 centroids. Find out the distance of each of the points with the centroid, and then whichever whichever point, whichever centroid is at a minimum distance, allocate that point to that particular centroid. And now we've got two clusters, ABD into one and CE into the second. Make sense? Does it make sense? The first set of iteration. Hello? Please say something. Otherwise, why we are spending time? I don't know. I've given you some initial my thoughts, right? How should do go about it? Again, there is no response. And sometimes I also feel, why should we? I mean, we're putting so much of effort, right, for you. If you cannot respond, then what is the fun of taking the lecture? In between, people leave and all, right? Again, Ali has moved out. No, he is there, but not responding. Shweta, Yamuna Krishnan, Vasu, can somebody please respond if you have understood? It's very simple mathematics. What should be the next step if you have understood? Ali, can you please respond? Okay, you have something going in parallel. Okay. Anybody else? Vasu, can you unmute yourself? And just tell me what is the next step? Say it's very. Have you understood what we have done? First, tell me, Vasu. Yeah, go ahead. Vasu, I'm unable to hear you. If you're speaking, I'm unable to hear you. Hello? Can anybody else hear Vasu? Okay, let me explain you. So this is the first simple distance calculation from the two centroids. Based on minimum distance, we have allocated the points. The next step is take the average of these three, come up with a new centroid. Take the average of these two, come up with a new centroid. You see, ABD average. So 0 plus 3 plus 2 by 3, 1 plus 0 plus 1 by 3, 1.66, 0.66. Next centroid. For cluster 2, it is 2.5, 4.5. Right? Now, what I've done is, you see ABCD was there. So another 2 points added, C1, C2. Right? So I am going to find out the distance of C1 from A. Again, using the same formula. Now my coordinates are 1.66 and 0.66 for C1. A we already have, that is given 0 and 1. So it is 1.69. To B it is this, to C it is this, to D it is this, to E it is this, to C1 is 0. I need not to find out from C1 to C2 because these are two separated clusters that we have. C2 to A 4.3, C2 to B 4.52, C 0.70, D 3.53, E 0.70, and C2 to C1, it is given 3.93. We can find it out even, yeah, we may not require to find it. Okay, now let us look at this. How should we allocate the point? I have 2 points now, C1 and C2. C1, let's check the distance of C1 with A, 1.69, C2 with A, 4.30. Since 1.69 is less, so allocate A to C1. Looking at B, C1 for 1.49 distance, C2 4.52. So again, allocate this to C1. For C, 3.35 with C1, 0.70 with C2, 0.70 is less, so C goes to cluster 2. D, 0.48 with C1, 3.53 with C2, so D goes to this cluster. C2, point D has 0.70 distance with C2, 4.54 with this, so this is allocated to cluster 2. So even in the second iteration, I'm coming up with the same clusters, right? There's no movement of points from cluster 1 to cluster 2. So I say that my algorithm is converged within single iteration here. If there is a movement of points, right, then I'll have to again do the same step. I'll have to recompute the centroids and again do it. So this is k-means clustering. Slowly and slowly the algorithm converges, right? And once there is a convergence, we say, okay, these are the number of clusters that I have. So one important thing that we need to determine is how to determine the value of k. K is the number of clusters that I want. The number of clusters that I want. How to determine the value of k? Should I come up with 2 clusters, 3 clusters, 4 clusters, or 5 clusters, right? So there is a method known as elbow method, right? Why the name is elbow? I'll tell you a few things about it, right? So there's a way. This is important to understand. Very, very important to understand. On one side, you see it is giving me some quality measure, right? And that value should be on the lesser side. On this side, I have the value of k, which is the number of clusters that I should count. Now, when I say the number of clusters as 2, right? It is some test that we did, right? Number of clusters is 2. That variance within the cluster, which is a quality measure, right? Don't go into the details right now, but you say it is higher. It is higher. The moment I move it to 3, the kind of clusters I've got, right? The clustering variance reduces to 50. From almost 750, it reduced to 50. And further, if you see, if I make it 4, it is reducing, but very minimal. Maybe from 50, it is moving to 40 or 30. And when I'm making it 5, even further, very less reduction, and even 6, it is lesser reduction. But the larger reduction you see here, right? From moving from 2 clusters to 3 clusters. So this is what they take. So where there's an elbow, right? The point which is at the intersection of the elbow. So this is kind of an elbow, right? It is making. Point at the intersection of elbow, k is equal to 3 clusters, is optimum for this set of data. That's what, I mean, the experiment on which it is carried out. So this step is also important to learn, right? So how do we do that? There's a numerical given for that, right? Already. There is also one guideline that you can set number of clusters as square root of n by 2, where n is nothing but your number of data points that you have in your data set. That's just a simple guideline, but you can also follow this within cluster variance and offline. You see that, right? This is the example. This is one-dimensional data, right? And if I come up with two clusters, assume initial centroids are 3 and 10. So these are the two clusters I'm getting, right? And if I take the variance is basically you take the mean of this 2, 3, 4, the mean is 3, you subtract it, right, from the mean. 3 minus 3, 3 minus 2, 3 minus 4. The mean of this could be 10 for the second, and you subtract it from the mean, and you're getting 732 as a variance, right, total variance. And when you make three clusters, C1, C2, C3, now you take the mean of this, and mean of this. So when you take that, this mean is still 3, this mean is 11, and this mean 20, 25, 30, this mean is 25, right? So you are reducing your variance to 57. Subtract mean from each of its a cluster. So within the cluster variance that you are reducing, and that's what the quality measure we are doing. There's a one more important quality measure that we measure is sellout coefficient also, which measures the quality of clustering. Again, a bit mathematical, right? But that's another thing. I'll check it out if it is within the prescribed syllabus. I can cover that. Even for knowledge sake, I can cover that. Not an issue. But yes, if you do some homework, definitely I can cover that. But that's a sellout coefficient that we use to measure the quality of clustering. And that relates to the basic definition of clustering. Intra-cluster distance should be minimized and inter-cluster distance should be maximum. Right? This is a bit about clustering. And with k-means, right, some drawbacks we do find. When you come up with these as original points, you see three different clusters, red points, green points, blue. But k-means can end up in these clusters, right? It depends on what kind of initial centroids you have chosen. If you have chosen different initial centroids, right, you may end up in different kind of clustering. That's a drawback, right? So if you have clusters of differing sizes, right, k-means may not give you appropriate results, right? If you look at this again, you can see well separated three cluster, one red, one blue, one green. But k-means may end up in this, right? And it is because of different density, right? Density here is different, right? So we have some advanced algorithms. So if you see this, these are the two natural clusters you see, one curve this, one curve this. But if you have k-means, it will end up in this kind of clustering. And this is one centroid, this is another centroid, right? So it is not a good clustering. It's a non-globular shapes. So we have other methods for that, maybe which is not prescribed as a part of applied machine learning. If you want to know, we can discuss at any point of time, right? But k-means is important, and from exam perspective, it is important, right? I'll maybe add this example, bit of mathematical example, right, which we have covered for your understanding, and then share the slide deck with you. This is okay from IDS course, maybe, yeah. So these are the slide deck that is available, right? So it's quite similar, right? Not very different. Why do we cluster? Summarizing data, some predictions we want to make, right? So this is again what kind of clustering that we are doing, right? This is the height, right? And this is the frequency. So height of black cherry trees. So how many trees falls in this particular height, right? 60 to 70 feet maybe, or 70 to 80 feet, and so on, right? So this is all clusters that we have built, summarizing data, predictions, right? Look at this. Clusters ask human to label the groups, right? So of course, when you have three categories of animals, cats, pandas, and giraffes, right? So groups algorithm will give you, but you have to label them, right? Because it cannot label them as like this is a cat, and once the clustering is done, what kind of label that you want to give to this particular group, what kind of label you want to give to second group, third group, and so. So k-means is the one which we have covered already. There is another one, Gaussian mixture model. It's largely theoretical, not in much detail, right? That we are going to cover this. Maybe I can spend maybe another 5 minutes more. Yeah, you have class at 11:15, right? And our first 30 minutes were largely about that. Okay, let me talk about the assignment part. I can take it next time, Gaussian mixture model, right? Let me talk about the assignment part. Have you seen the assignment? How many of you have seen the assignment? It's important. How many of you have seen the assignment? May I know how many of you have seen the assignment? Quick answer, please. I know in brief, have seen the assignment, but I have not gone through it yet. Okay. What is your understanding? So far, I mean, what is your understanding from the assignment? Okay, let me share. I've downloaded it. I've downloaded it now. Just listen quickly, right? Some instructions, right? Please go through it. It's a group assignment. People who have given us the groups might have been be added into the same. But if you haven't given any group, uh, Professor Omshiri has allocated, might have allocated you to some group, and now that groups cannot change. That's the number one thing, right? We've given you enough time for that. So now groups cannot change. You have to submit it in groups. Uh, Learning objectives. Supervised machine learning techniques you have to apply to solve a classification problem, right? Build and compare classification model suitable for business decision making, right? So this is what we want you to look at. You do data pre-processing, exploratory data analysis, feature engineering part, random forest ensemble, model evaluation, and business interpretation of results. That is what is largely we want you to do. And the constraints are the data set should originate from students' workplace. That will be better, right? Wherever you're working, right? Um, if you have a data set from there, it is good. Or you can also pick up some realistic industrial business problem domain with, I mean, which matches your domain. Don't pick up any random data set, right? For workplace data, it cannot be shared due to confidentiality, and equivalently publicly available dataset from the same domain may be used. It is mentioned. Dataset should contain at least 10,000 instances, 8 input features at least, right? More is value fine, and it should involve classification. Students should briefly explain how the chosen dataset relates to their organization or the industry in which they are working, right? This is what you need to mention as when you will make submission. What are the tasks that you need to apply? Understand the business problem, identify the classification objective first. Why you want to classify, what it will give you, and that should be in line with your organization where you are working, right? perform exploratory data analysis to understand the characteristics of the data that we have also mentioned as a part of core concept, right? Clean and pre-process the data, handling missing values, categorical variables, class imbalance, feature selection, and all. Apply suitable feature engineering techniques, right? Then random forest and ensemble classifier you need to apply. Evaluate the models using the appropriate performance metrics. For classification, we know, right? Accuracy, precision, recall, confusion metrics, and all those things you can evaluate for the different classifiers, right? Two should be mandatory there, and recommend which is most suitable for deployment at the workplace. And with a reason, of course, discuss the practical challenges that may arise while deploying the solution in an industrial environment. So this is what these are the marks, right? Anchor, apply, analyze, all these you need to write. And of course, there is a reflection point which you need to submit, reflect, right? What constraints in your organization would change your approach? Maybe if you see, okay, this is what it is that this classification helps me in certain way, right? But can you apply it directly to the organization, right? And with respect to these, what are the challenges that you can talk about, right? Or what these are the constraints, right? It could be data, it could be privacy, scale, regulations, technology stack, would change it. So basis this, how you would deploy, right, at your organization if you have these kinds of challenges. What is the single most important improvement before this could be used? I mean, what improvement do you suggest if you want to use it at your workplace for something, to classify something? What is that improvement that you would like to make, right? You have to justify your answer. Now these things may be different for different people, right? Because maybe the role in which you are playing is different. So this point, everybody can write it, right? A 4-member group, I can see 4 different answers of it. It's completely fine. Write your ID that this is my answer. These are the questions, right, that you need to answer for analyze part. Which classifier performs best and why? What is the evaluation metric? Which is most important evaluation metric? So this I have added so that it helps you, right? So you can submit a Jupyter notebook, you can submit a PDF file, right? You have to add this also, each one of you. Name, ID number, the domain in which you are working. Domain should be functional domain. Are you working in for a retail sector or a telecom sector, for banking and finance? Or so we are capturing that kind of domain. Don't say I'm working as a support engineer or something like domain, right? Maybe you are providing support to life sciences, right? Maybe you are providing support to a retailer, right? So that is expected. We do have a choice to apply classification technique. I've mentioned 2 models, right? Others are already covered in the lab sheet. Ensemble and random forest. These are the 2 you have to apply. Compare both also. You want to compare more, you are free to do that, right? But these 2 should be there. So appropriately justify. Don't pick up any data set, anything that you have picked up and you are applying that. No. So this reflection part is very, very important, right? This will also carry marks. Reflection part is important, it will carry marks. Viva will be there, of course. After that, we will plan a Viva also from maybe next session onwards. So that I will allot you some time and you have to be present there, right? Let's have a discussion about it. It will be an open discussion, not a very fair very kind of a strict evaluation, right? But I just want to know your understanding and all, right? Why you have put this, why not? So you will submit an assignment, you should know it better. That's all I'm looking for. You have proper rationale behind doing everything, that's fine. So that's all from my side regarding the assignment. If you have any questions, you can write to me or write to Professor Omshri. Mark a copy to me also, right? Anything else that you want to ask? Lakshmi or Vasu, you have gone through the assignment. Oh, okay. Go through it. Don't delay this because it should be related to your workplace. Have meetings among yourself and then start with the assignment, right? Learning should be there, right? That's what is more important. Learning should be there. Now she will conduct a session, right, on clustering techniques also, maybe in the next session, which is I think scheduled on next Sunday, not this Sunday. And then there will be another lab sheet coming up. So you will see one quiz coming up this week, right? Assignment is already given to you, and there will be one more lab sheet that will be coming up for this unsupervised learning, and maybe we'll see if we can include artificial neural network bit up into it, right? So you're getting a flavor of
Sir, for
everything.
the
Yeah,
sir, am I audible now?
yeah, you're audible.
Sir, for the EC1 component, what other things are left? Like now we have only one assignment, one lab sheet, and one quiz left, right? Or
Right.
are there other things as well?
Viva also along with the
Yeah,
assignment.
Viva, I thought that it is covered in assignment only, but
Yes,
these are the
yes,
only things, no?
yes. Because Viva will be obviously after submission. I will give the Viva dates, right? So you can attend. You can have weekdays, late evenings, right? And maybe on Sunday we can spend some time. I'll find out that how we have to do that. Why? Okay.
Okay, sir.
There are 4 members, so maybe you can see 5 to 8 minutes per group, depending on how they're discussing, right? But do this generously, this assignment. Don't put here and there and any random thoughts and come up with this. So we will give evaluations also based on then the Viva, right? Majorly that I want to focus on those aspects. I've clearly mentioned right in the assignment. Reflection part is important. Do pay attention to that. Okay, all right. Implementation, I know people can do it easily, right? But understanding why this, why that, that is important. Anything else that you want to know? Are we good with the things? I think your other class might have also started, so you can definitely join that. Anything you want that I should look into, please write back to me. Any doubts related to assignment, anything conceptually you are feeling it hard to understand, please write to me.